transition frequency scales as 1 over n cubed. So that wavelength that's going to cause transitions around this n is going to scale as n cubed. So that's okay. Right? So this is what motivates us to use a dipole approximation. But you need to remember that because this classical radius scales as n squared, okay, so the dipole approximation is not always valid. So the dipole approximation, what it tells us is that we are working in a scenario where the wavelength of the radiation is much greater than A naught. Okay. So this is equivalent, is much greater than R. Okay. This is equivalent to saying that K times R is much less than 1. Okay. Right? So this is the long wavelength approximation. Okay. When K times R, this is like K dot R is much less than 1 because they're only going to differ by a factor that's about 1. Okay. So now, under the long wavelength approximation, I can approximate the electromagnetic field. If I think about a vector potential that looks like a plane wave kind of vector potential. So this would be RT. Okay. Let me reference everything first to the nucleus. Let's say that the nucleus was located at R naught. Okay. So I'm going to reference everything to R naught plus R. Okay. And this is some kind of a plane wave, which is there is a temporal part, and the spatial part is simply I K dot R naught plus R. Okay. So what this long wavelength approximation allows me to do is to say that this is basically just e to the I K dot R naught 1 plus K dot R plus etc. Right? And since under the long wavelength approximation, this is much less than 1. I'm just going to approximate the vector potential to be only a function of time. So effectively, the atom, the electron in the atom only sees the vector potential at the origin. And this is a long wavelength approximation. Under this approximation, the classical Hamiltonian is roughly equal to P minus E A at R naught 2 squared plus Okay, so the next step is to turn this into the quantum mechanics. So by turning this into quantum mechanics tells you that we replace this with H bar over I gradient, right? Okay. So now, what time is it?
10:51 on my watch.
Okay, maybe I just talk next time. So let me just give you
Summarize.
an overview of where we're going. Okay. So we're going to reduce this Hamiltonian into a effective dipole coupling. Okay, basically turning this P minus A squared thing into a E dot R thing. Okay, and this requires us to do a similarity transform for the wave function. Okay, and I'm going to tell you how basically think about this. Previously, if we had just a normal Hamiltonian, it's something like H equals to 1 over 2mp squared plus d, right? So the effect of coupling to the field in the long wavelength approximation is just that in any approximation, it's just you change the momentum, right? Okay. So we know from quantum mechanics that the momentum is conjugate to the position, right? So if I make a change in momentum space, okay, what do I get? If I shift the momentum, I get what in x domain, in x space. Think about Fourier transform. If you shift in one domain, the other one is frequency phase, right? Okay. So basically, if I had a wave function that is like psi of x, that's the eigenfunction of this, I know that this is just going to be, eigenfunction of this thing is just going to be what? Psi of x e to the I EA over h bar, something like this, right? Okay. And when we plug this into the Schrodinger equation, you'll see a term like this, a effective interaction coming out. So that tells you why we can use the dipole interaction. And then after using the dipole interaction, we're going to quantize the system by quantizing the electromagnetic field, this E thing. Okay. So you've seen in chapter 12 how we turn this E into operator. Right? And from there, we'll derive a Hamiltonian that's fully quantized. And using that, we're going to study quantum systems where you have either a single atom coupled to a single mole, or a single atom coupled to a bunch of trapped moles. And you can think about also when the field is exactly resonant with the atomic transition, or when they're slightly off resonance. So this will take us about 2 lectures. This is not ion trap, but it turns out when I quantize the Hamiltonian, that Hamiltonian looks very much like the ion trap. So that's called the James Cummings Hamiltonian, and the ion trap Hamiltonian is similar. Whenever you have two-level system, and you have a field, it's that Hamiltonian. All right, so I'll see you on Tuesday, and you have a homework this week. I'll probably hand it out over the